Okay, so today we're going to do linear programming. And so on this one, what I recommend you doing is there's a worksheet, kind of looks like this. You can download it from PowerSchool. So if you go to my PowerSchool page, right here under Chapter 3 Syllabus 3.4 Learning Linear Programming 2020, that's your notes for today. So you can, if you print those first, it makes it a lot easier to do the lesson on the notes there. Also, your quiz is posted as assignments, so just know that going in. So let's work on this first problem here. So I think the first one looks kind of like this. Let me get it so I can size it a little bit better. Okay, so this is the lesson basically. So you're going to go ahead and first of all, let's just look at these two. We talked about these the other day. Like that is basically saying, what quadrant are you talking about? Well, we're saying x and y can't be negative. So notice here, I pretty much only drew the first quadrant. I kind of cut off the axis. So that's the line x equals 0. This is the line y equals 0. It's a horizontal line. It's basically saying all the y values, all the x values are going to be positive. So this is all in quadrant 1 right here, which is where it is. Let's graph this other one here. So let's graph this one. The y-intercept is 3. Slope is -1 over 2, so -1/2, so down 1 over 2, down 1 over 2. Draw a solid line there. I'm going to shade down eventually because it's less than. It's kind of a triangle right now, but I want to include this last shape in there. So we're going to do this one next. So that one's going to be y-intercept of 5, slope of -1. I like that it goes through right that nice point right there. And go ahead and graph your line. And so this one also is shading down because it's less than. So the solution region is just below the blue line and below the green line there. And also only positive values or 0 or more for x and y. So I'm not including anything other than the first quadrant. So that's really my graph there. What you want to do is identify the vertices. And there's 4 of them in this case. So 0, 3, 4, 1, 6, 0, and 0, 0. I'm guessing 0, 0 is not going to be a maximum of our function, but let's just test all 4 vertices of the feasible region there. So we're just testing it by plugging into this equation, and we can pretty much do this by hand just because it's smaller numbers. So this would be x, which is 0 in this case, plus 3 plus 2 times y, which is 3. So I get 6. This one, when I plug it in, it'll be x, which is 4, plus 2 times y, which is 1, which is also 6. That's unusual. And this one would be 6 plus 2 times 0, which is 6 plus 2 times 0, which is 6. Let me just double check this. 4 plus 2 times 1. Oh, be careful. I thought something was wrong. So for some reason, I put that point right there. But the feasible region actually trying to erase that point. Let me see. That is not what I need there. So I need the endpoint of the feasible region, which is 5, 0. That makes a lot more sense. And so when you plug in 5, 0 into the equation, you get 5 plus 2 times 0, which is 5. And I guess we'll plug in 0, 0, but it's really kind of unnecessary. 0 plus 2 times 0, which is 0. So we want to maximize this function. So that looks like 6 is the maximum. And the points that lead to that maximum would be 0, 3, and 4, 1. So those are the best options for you. This one, again, we start with restrictions. This basically says first quadrant. Solve each of these other guys for y. So this one would be y is less or equal to negative x plus 8. So slope of -1 here. Oops. Looks something like that. And let's do this one. Slope. So this is y is less or equal to negative 2x plus 10. 10 is right up here somewhere. Negative 2 over 1. Negative 2 over 1. I guess I'll go all the way down to the bottom there. Oh, it goes right to here, doesn't it? That's nice. Okay, so if the slope is negative 2. So then we want to maximize that function, so we have to find the vertices of the endpoints. So this is the endpoint, this is the endpoint, this is a vertice, this is a vertice. We're shading essentially inside of here, right? Everything there, here, all up to that. Kind of curves a little there. So that's our feasible region. So we're only really concerned about the endpoints when we plug them into our objective function here. So this is 0, 0, probably not going to be the answer, but we could see this is 5, 0. This is 2, 6, and this is 0, 8. So we're just going to plug into our objective function here. So our objective function is this one. So this would be, in this case, 100 times 0 plus 4. This one is 2 plus 40 times 6, which is 200 plus 4. And this one would be 100 times 5 plus 40 times 0, which is 500. This one's going to be 0 probably. 100 times 0 plus 40 times 0 is 0. So what's the best choice here for the maximum? We need to maximize this, so it would be 500 is the max, and the ordered pair that leads to that is 5, 0. Just want to show you this last one just because it's got a little twist on it compared to the others, but I think you're almost ready for homework, to be honest here. So let's do this one. So it's kind of interesting. I hope you see that like an x equals line is a vertical line. So we actually, well, we should probably start by just kind of numbering some of this. So here's what I mean by that. So that like this might be 20 every 2 tick marks, maybe is every tick mark is 10, 40, 60, 80 or something. I'm going to do that to the x-axis, y-axis as well. 20, 40, 60, 80. Okay, so let's graph this function here. So it's a vertical line at 20 and greater than that, so arrow or shade to the right. It's a vertical line at 70 and shade to the left. So it's inside of those two blue lines. This one is going to be horizontal line at 60. It's going to be below this line because it says less than. And I might have to do a little bit of work for this one. So you get 12y greater than or equal to negative 8x plus 720. Divide by 12, you get y greater than or equal to greater than or equal to. I guess that'd be negative 2/3 x plus, I think that's 60. So I got 60 is the y-intercept, slope is negative 2/3. I scaled them the same, so I'm going to go down to even though it's 20, the right 3, even though it's 30, because it's the same ratio. Down 2 over 3, down 2 over 3, and you've got this. So the region I need to shade here, the feasible region, kind of looks like this. Because again, we're shading below the green line, above the maroon line, and in between the two blue lines there. And so my order pairs for those. This one's tough, so I've got to figure out where that one actually hits. I'm not sure exactly, but we'll find out. So this one's easy, right? This is 20, 60. This one is 70, 60. This one's not too bad, actually. It's 20, 40. It seems to be labeled nicely. But this one doesn't seem to hit at a nice point. I do know the x value is 70. So I don't know the y value. So one way of finding that is actually to plug into the function. So that's the kind of maroon line. So if I plug in right here, if I plug in 70, so let's do that. Let's get our calculator out and do that. Oops. So get a calculator. It's this one. So negative 2/3 times 70, I guess. We know the x value plus 60 is 40/3. Okay. So we've got 40/3. And so we're going to plug in these values into the function here. So this is we want the minimum value for this one. Interesting, I didn't pay attention last time. So the minimum value on that one. Usually we're looking for the max. So this would be 8 times, I'm going to do this in the calculator just to ease it up a little bit here. So 8 times x plus 5y, let me write that down. 8 times x plus 5y is the function to be maximized. So this would be 8 times 20 for the first point. Whoops. 8 times 20 plus 5 times 60. Okay, and so that would be 460 here. And then 8 times 70. Whoops. In the calculator, 8 times 70 plus 5 times 60 is 860. That's a lot more. So let's see, 8 times 70, that bottom right point, plus 5 times the fraction 40/3. If I want to get the decimal there, I can hit Control Enter to get it. That would be 626.667. 666 repeating, I guess. And then the last one would be 8 times 20 plus 5 times 40. It's 360, so this one's 360. So which one minimizes the function? It looks to me like the minimum value is actually 360, not 460, not 860, not 626, and the point that causes that is the 2040 point. So pay attention to whether minimum, maximum. I'm tempted on that problem just to go ahead and jump to the largest because that's what we usually do, but sometimes we minimize. So in that case, we're minimizing. That's the lesson.